Hello everyone, this is Dodge. Today I would like to talk about an interview coding question, Leetcode 210. This is a topic about topological sort. I will cover two different approaches to solve this problem, Kahn algorithm and DFS algorithm. I will also talk about building graph using different interpretation, must come before graph versus depends on graph, and we will use Java to do the coding. There is also a bonus at the end of this video, where we will talk about the follow-up question for this problem. Okay, let's get started. Let's first look at the problem description. We will have a total of n courses. They are labeled from 0 to n-1. We will have another two-dimensional array prerequisites. The ith element of this prerequisite will be an array with value ai, bi. It means you must take the course bi before the course ai. Here's the interesting part. For this problem, we can build our graph using different interpretation. We can define a graph with an edge from bi to ai, means bi must come before ai, like this green part illustrate. The other way is we can define a graph with an edge from ai to bi, means ai depends on bi, or ai's prerequisite is bi, like this yellow part illustrate. They are kind of the opposite, or the reversed concept of each other. A similar way to understand this is we can sort array using ascending or descending order, depending on how we define comparator used for sorting algorithm. This is similar here. We will see later how we utilize these concepts in the coming problem-solving process. Let's look at the input and output of this problem. The input have two parameters. Number courses. Here the example value is 5. The two-dimensional array prerequisites, indicating the relations of those courses. The output will be an array of sorted courses. There may be multiple valid answers like this one. You just need to output one valid answer. Okay, normally for those kinds of problems, we want to draw a graph on paper to help us better understand the relations to those courses. Here we have courses from 0 to 5. I draw this graph with the green line arrow. The edge from 0 to 1 means 0 must come before 1. This graph is much more illustrative than the original one two-dimensional way, but it seems still hard to figure out how to solve those courses. Let's try to rearrange this graph a little bit. By the way, this is a must come before graph. Here is the updated one. Is it clearer than the previous one? From the left, we can see course 5 does not have any prerequisites, so course 5 can be scheduled first. Let's use this graph to perform a manual problem-solving process. We will mark scheduled course as red to distinguish it from others. Here 5 is scheduled. We mark 5 as red. After 5 being scheduled, we should review all the courses that have 5 as their prerequisite. Those courses are the outgoing neighbors of course 5 in this graph. They are course 3 and course 4. So we updated their prerequisite that course 5 is not a prerequisite for those courses anymore. Then we can see course 3 has no prerequisite anymore, while course 4 still have one prerequisite, which is course 3. So the next scheduled course can be course 3. We schedule course 3 and mark it as red. For the following same process, we update the prerequisite for the outgoing neighbors of course 3, which is course 0 and course 4. Then both of them do not have prerequisites anymore. We can schedule both of them in random order here. Then we update the outgoing neighbor of course 0, which is course 1. We also update the outgoing neighbor of course 4, which is course 2. Now course 1 is ready to be scheduled without any prerequisite. We schedule course 1. We then update the prerequisite of outgoing neighbor of course 1, which is course 2. We can now schedule course 2, and finally all of these courses have been successfully scheduled. Problem solved. If we review this graph, it is just a topological sort, with each course under the certain bucket separated by white dotted line, and the topological sort can be solved by Kahn's algorithm, which was first described in 1962. Let's have a glance at this Kahn algorithm using this pseudocode. We define L, representing an empty list that will contain the sorted elements. We define Q to be Q of all nodes with no incoming edge, which means integrity equals to 0. The logic starts with a while loop. When Q is not empty, we will remove a node from Q and add this n into the result list. Then we will traverse each node m that have an edge from n to m, or simply the outgoing neighbor of this n. We remove edge e from this graph, which also decreases the integrity of m. If m has no longer incoming edges, or the integrity value of m is 0, we insert it into Q and repeat this while loop. After we finish this while loop, if this graph still have edges, it means graph have at least one cycle. We will return error. Otherwise, we will return L, which contains a topologically sorted order. Okay, let's add some data structures and go through this problem solving again using Kahn's algorithm to see how it goes. First, we put all nodes that integrity is 0 into Q. For this example, we only have node 5 with integrity 0. We put 5 into Q. Then we process this node 5, mark it as red, and put it in the result list L. We update the outgoing neighbors to -1 for those integrity. This leads to course 3 meet the in-Q criteria of 0 integrity. We put 3 in Q. We process node 3 and put 3 in the result list. We update outgoing neighbor of node 3, then we put 0 and 4 in Q. We process 0 and 4, put them into result list L. We update outgoing neighbor of 0 and 4. Then 1 is ready. We put 1 in Q. We process 1 and put it into result list. We update the outgoing neighbor of 1, and now 2 is ready. We put 2 in Q. We process 2, and the Q is empty now. We notice there is no edge in this graph, or we can use another way to determine this, by checking whether result list L contains all of the nodes of graph or not. If the result list contains all of the nodes, which means we get the successful result. If the result list does not contain all of the nodes, it means for those nodes not in the result list, there must be a cycle inside them. So when is it impossible to finish all courses? As this example shows, when Q is empty and L does not contain all nodes, we can see in this scenario, we could not find any node that has 0 in degree. There is a cycle among 3, 4, and 5. Okay, talk is cheap. Show me the code. Now let's do the live coding. Here is the method signature for this one. The output is the int array. The input has two parameters, name, courses, and prerequisites. First, we will define a queue. Then we need to build the adjacency list map for this graph because the original input is not quite easy to be used. So let's define a map here. The key will be the course number, the integer. The value will be the list of the integer, which means that it's the adjacency list of each of the node. We need to do the initialization for this adjacency list map. we simply put the empty array here. Then we need to have an in-degree array to store the in-degree numbers of those things. We do not need to perform the special initialization because the default value is 0 here. We also will have a list of the integer to store the result. Then let's fill the adjacent list with the prerequisite value. For all of the one-dimensional array P inside the two-dimensional prerequisites here, we know that it has two values, P0 and P1, and it means that we should take the P1 before P0. So in our must come before graph, which means there's an edge from P1 to P0. So P1's adjacency list should contain P0. Now it's clear. P1 dot add P0. Also, it means that the in-degree of the P0 should plus 1. And then we need to iterate through all of the courses, find the initial courses which have the 0 in-degree. We will check if the in-degree I equals to 0. Then we need to put them into queue. And now this is the magic logic. While queue is not empty, we will first pop a result from the queue. And this one means it's ready to be put in the final result here. Then for each node, inside this current one's outgoing neighbors or the adjacency list, because the current one has been removed, the in-degree of those should be -1 accordingly. And then if some of them being updated to 0, means they are ready to be put into the queue. After we have done all of this, we will check if the result.size is less than the number of courses, which means that we have done our best but still could not get all of the result, means there's a circle inside it. Based on the problem requirement, it asks us to return the empty result, so we return new int array with 0 value. If not, we need to return array. Here we need to do some tricky part. The one we are using is the list of array. To change it to the normal array thing, we can use the Java add stream operator and map to int. Do it like this one. And now this should be good enough. Let's first look at whether this can pass the Leetcode online verification or not. Let's copy all of it. Okay, here is our Leetcode. Let's copy paste it on here. Let's click submit. Okay, you can see here is the result here. It has been accepted. Let's further look at its time complexity and space complexity. Because for this one, the time complexity, we go through all of the nodes, and also inside this node, we will go through its outgoing neighbor. So we basically iterate through the number of vertices and number of the edge for the graph. So the time complexity should be the OVE, V plus E. V is vertex and E is the edge. And for the space complexity, the additional space used here is that we build additional map which contains all of the vertex and all of the edges. Other than that, we will have the result and we will have a queue. So the space complexity should also be the same, OV plus E here. So that is the overall solution for the Kahn's algorithm. Okay, problem solved. But do we have any alternative way to solve this? Definitely is. We can also use DFS approach, which full name is depth first search. So as I mentioned earlier, we will try to build a graph using different interpretation that depends on graph. Edge from 1 to 0 means 1 depends on 0. How do we solve this using DFS? Let's first look at the classic DFS algorithm pseudocode. We will have a method DFS which will recursively call itself to traverse all the outgoing neighbors of current node, and then we will add n to the result list last. Basically, we will always put prerequisite node into result and put current one later. This can ensure all courses current one depends on will be scheduled first. But how to prevent same node being processed twice in DFS? Easy. We can mark node as visited. Then, when is it impossible to finish all courses in the DFS approach? We can detect the cycle in graph. But how to detect the cycle in this graph? Can visited flag solve this issue? Let's try with an example. Here we have a simple graph 0, 1, 3, which apparently has a cycle. We have white state, means the initial state of each node. We define a blue state, indicating node starts recursion, and means node has been visited. We first visit node 0. We mark it as blue. Then we traverse the outgoing neighbor of 0, which is node 3. Node 3 is white, which means it is not visited yet. We can start the processing of node 3. Then we mark node 3 as blue. We follow the same logic to traverse outgoing neighbor of 3, which is 1. 1 is white. We can process 1. We mark 1 as blue. Then we traverse outgoing neighbor 1, which is 0. Oh, 0 is blue, which means it has been visited before, and we detect a cycle. Cool, but let's look at another example to see whether this approach can always work or not. Here's another example, still 3 nodes, but with no cycle inside them. We start with node 0, mark it as blue. We traverse from 0 to 3. Then we mark 3 as blue. Since 3 has no outgoing neighbors, we will trace back to previous node 0. Since 0 also we traverse all its outgoing neighbors, we will move on to the next node 1. Some extra explanation here. For DFS, since this is a graph, not a tree, we need to traverse all nodes of graph so that we can ensure we cover all the nodes. For this example, we simply follow the numerical order to visit 0, 1, 3. After 0 is done, we will visit 1 next here. We traverse the outgoing neighbor of 1, which is 0, and 0 is in blue status. Did we detect a cycle here? No, but why our previous approach does not work here? It is because a cycle should only exist when a node has been visited again inside its current DFS recursion. And we should add another state to indicate the end of the node recursion. Let's do it again, with the new flag red, indicating node ends recursion and is put to result list. We still start with 0, mark it as blue first. We go from 0 to 3. We mark 3 as blue. 3 has no outgoing neighbors, so we end the recursion 3, mark it as red. We trace back to 0. We also traverse all the outgoing neighbor of 0, so we mark 0 as red. Then we start the process 1 and mark it as blue. We traverse from 1 to 0, and since we know 0 is red, so it means we can just ignore 0, and no cycle is detected, as expected. So here is the updated DFS pseudocode with 3 states. First, we define a list L to store result, and then we iterate all the nodes in this graph, perform DFS. Inside the DFS method, we will check the current node. If its state is red, means its node has been fully processed, and we can safely ignore this. If its state is blue, it means we detect a cycle. We can stop further execution. If none of them, it means this node is in white state, and we should process it. Then we first mark it as blue, and start the processing and recursion of it. We will traverse all its outgoing neighbor nodes, do DFS for each of them. After that, we consider this node is done the recursion, and mark it as red, and put it into the result list. Okay, let's go through this DFS approach step by step here. The right part of screen we have a purple rectangle, which contains the stack trace of method calling. The bottom right we have the result list, and we are using the depends on graph here. We first start with DFS 0, marking it as blue. Then we traverse outgoing neighbor of 0, which is 3. We start the DFS 3. We mark 3 as blue. Then we start the recursion of 3 and go to its outgoing neighbor node 5 and start DFS 5. We mark 5 as blue and start processing node 5. Since node 5 does not have any outgoing neighbors, we finish the processing and mark 5 as red. We will put 5 into result list. Then we trace back to previous node 3. Since we finished the only outgoing neighbor 5, we finish processing node 3. We mark 3 as red and put it in the result list. Then we trace back to node 0. Same logic. We complete the processing 0, marking it as red, putting 0 into result list, and we start the next node 1. Then we move on to the next node 1, marking it as blue. We process node 0. We notice 0 is red, so we can simply ignore 0. Then we trace back to 1. We finish 1, marking it as red, and put 1 in the result list. We start DFS 2. We mark 2 as blue. We process its outgoing neighbor node 1. 1 is red. We ignore 1. Trace back to 2. And move on to next outgoing neighbor 4. We mark 4 as blue and traverse the outgoing neighbor of 4, which is 3 here. Since 3 is red, we ignore 3. We trace back to node 4. We traverse the outgoing neighbor of 4, which is 5. 5 is also red. We trace back to 4. Then we complete node 4, mark the 4 as red, and put 4 into result list. Then trace back to 2. Complete node 2, mark it as red, and put it in the result list. Okay, let's do a live coding now. So here is the same method signature. And to solve this issue, we will first define some state using the integer. White equals to 0. And then blue equals to 1. red equals to 3. We also need a Boolean global variable to indicating whether we find a circle or not. If we find, then we do not need further execution. Now let's look at the implementation logic here. First, we need an array of the state. We do not need to perform the initialization because the default value is 0, which is white. We also need the adjacency list to make it easy to be used here. And we perform the initialization for this adjacency list. Put the empty array list here. And then fill the prerequisite result into this adjacency list. Let's check it again. P0, P1 means P1 must come before P0. It also means P0 depends on P1. In this depends on graph, which means there's an edge from P0 to P1. So now it's clear. Dot add P1. For DFS, we need to iterate through all of its nodes here. So there's a for loop to do this work. And then we need to write our DFS signature method. The input of the DFS, we first need this adjacency list map here. And then we need what is this current node and the state array and the result. We also forget to define the result list here. Okay, so inside this one, as I described earlier, first we'll check whether it is possible. If it's not possible anymore, we simply return, do not perform any execution. Then we will check the state. If the state is red, it means that we can safely ignore this one. If the state is blue, which means that we detect the circle, we change the global variable is possible equals to false, then we return. Then, if we can continue, which means the state is white, the first thing we need to do is to mark the state as blue. And then we need to traverse all its outgoing neighbors inside this adjacency list map. We will do DFS again with the node as current value. Put all of the things here. After we have done all of this, we need to change the status to red and add it into the result. That's all for DFS. Then we move on to our main function here. We will put the adjacency list, current node I, state, and result. After we have done all of this, we simply check if it is possible or not. If it is not possible, then we return the empty result, the new int with 0. Else, we return the final one. Similar stuff, I'm using the list. The question is asking us array. We do a conversion here. String. And that's it. Let's copy this result into the Leetcode to verify it against the verification. Okay, let's copy paste it here. And let's click the submit. Okay, I have some typo. Let's fix it and submit it again. Okay, it passed the verification. Cool. Let's also look at its time complexity and the space complexity. So for the time complexity here, we traverse all of its nodes and its vertex. And also inside its traverse, we will check each of its adjacency list. So basically, we will also cover all of the vertex and edge. So the time complexity should be the OV plus E. For the space complexity, since we also build this adjacency list, it will cover the vertex and the edge. And after that, we will have the result list and have the state, which is the vertex number and some stack calling one, but we do not count it in the space complexity. And so the space complexity should also be OV plus E here. Okay, good interview coding question normally will have follow-up question. What can be a follow-up question for this problem? Here's one. Can you return the list of lists so that the calls can be taken in parallel or grouped together in a list? Let's look at the example again. When can calls be taken in parallel? For this follow-up, Kahn's algorithm solve it easier than the DFS. We can say in this example, the purple rectangle part, cos 0 and cos 4 can be taken at the same time. How to update Kahn's algorithm for this follow-up question? First, we need to update the output to be a list of lists. Then, inside this while loop, for each execution, all the nodes in the current queue have in degree 0, which means all of them can be processed at the same time. So we put all of them in a temporary list, and add this temporary list into final result list, and then follow same logic to process each node in this temporary list. And that's it. And let's do a live coding again to see how we change it in the original Kahn's algorithm solution here. Okay, here is our previous Kahn's algorithm implementation. Let's first change this output from the array to a list of list. And then we also need to change this result here, list of list. And then we need to do something here. So when queue is not empty, we will define a list, we call it temp list. And this temp list will get all of the result from the current queue. So I will use this way to get all of it here. Then we will clear all of the queue here. And the result, we will add this temp list. And then for the current value, we will get it from the temp list. And after that, all of the values should be the same. And we also need to change the result a little bit. Since we have the list of lists, in order to check how many of the calls is here, we need to have the counter to do this stuff. So I define this sort call sorted courses here. And the sorted courses every time will plus the temp list size. And the result, if the sorted courses is less than the name course, then return empty. Otherwise, just return the result here. To perform some testing, let's put some test data here because there's no OG can help us, so we need to do it by ourselves. This is the sample one. Let's run to see how it goes. Oops. Oh, yeah, I need to remove this line. It should be ready to go. Oh, yeah. I need to return the empty list here. Now you can see, as mentioned, this in parallel one has been output correctly as expected. Okay, that's all the content for this video. If you like it, please give a thumb up. If you want to stay tuned, please subscribe to this channel. And see you next time.